Greetings, everyone. My name is Dr. Charles Parker. I'm the VP of Machine Learning Algorithms here at BigML. And this is the first of the personalized training sessions that you're going to have with various staff at BigML, where we're going to teach you a little bit more about machine learning in general, and also about how the platform works and how you do machine learning with BigML, and some of the ways you can be more effective with machine learning by using BigML in the way we intended it to be used. A few reminders before I get started with this first session. First of all, you're all on mute right now. You're all muted by default. If you have questions during the presentation, I'm going to try to make silence during the presentation so you guys can raise your virtual hands or type questions into the chat, into the GoToMeeting client. And if there are a lot of questions in the chat, there are several other staff people from BigML on right now, and they will interrupt me during the presentation so that I can answer those questions as we go. Also, you'll all be getting both the slides that I'm showing right now and also video of the presentation, so you can watch it over and over again if you miss something during the presentation. And finally, your VPC, the A1 Digital VPC, our deployment of BigML behind your firewall is up and running right now. I'm going to try to run the demo bits of this presentation using your VPC, and you will all get credentials for that VPC, so you can log in and play with it very soon. All right, so with that, let's get started. I call this first session a gentle introduction to machine learning. And what we're going to do here basically is, first of all, I'm going to go through machine learning in general. I'm going to go through a motivating example, and then I'm going to talk about just what is machine learning. This might be review for some of you. What is machine learning? When do we do it? And how does it basically work? And so that's going to take up most of the time in this session. And then after that, I'm going to get into a little bit more of the BigML specific machine learning bits that we've developed for people to use on our platform. So I'm going to start out with machine learning in general, and then kind of get more specific as we go along, and then start to use the platform in the back half of this training session. And so here's a little outline that we'll see as we go. First of all, I'm going to start with a motivating use case, a little machine learning fable, and then I'm going to talk about machine learning in general, give you some intuition about what machine learning is and how it works. After that, we'll go through in a little more detail the basic idea of machine learning, which is you're creating a program from data. When we do machine learning, we're actually doing computer programming with the data that we have. And then kind of drilling even further down, I'm going to talk about modeling, what that means. In particular, I'm going to talk about supervised machine learning modeling. And then we're going to do a little bit of it in the BigML interface. And see what that looks like, play with the BigML model visualizations a little bit. Step 6 there, we're going to go in finally a little more detail with the model. What more information can you get out of the model once you've created it? And then finally, we'll go to evaluation. So once you've created a model from the data that you bring to the platform, how do you know if it's any good? How do you know if it's doing what you want it to do? So let's start with the little machine learning fable. So let's imagine that, whoops, that didn't work very well. Let's imagine that you're the CEO of a mobile phone service. Congratulations, I'm sure you worked very hard to get where you are today as the CEO of this mobile phone service. And let's imagine that some percentage of your customers leave the mobile phone service every month. And people in the industry, they call this customer churn. Every month, some of your customers decide not to renew their subscription. And so what you want to do is you want to reach out to the customers that you think are going to leave next month. But of course, you don't want to call all your customers. There are too many, and that would be too costly. So you want to identify these customers that you think are going to leave the service next month. You want to make a prediction about who's going to leave the service, and you want to reach out to just those people. And so the question, of course, that you're faced with is, who are these people? How can you find the needle in the haystack here? How can you find the people who are most likely to leave the service? And so a good thing to do with all problems like this, before you even think about machine learning or what the data looks like or blah, 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 you want to begin with the end in mind. So what do you currently do to identify these people? You probably have something in place. And are you measuring the quality of that thing? So let's say currently you use some kind of simple targeting strategy that identifies the 10,000 customers that are most likely to churn. And let's say that's 5% of your customer base. So for every 5 people you call, let's say 2 are actually considering leaving, 4,000 or 40% of those 10,000 people. And for those customers, the operators can convince half of them to stay. So your operators are effective about 50% of the time. They make some promotion. They say, hey, if you stay with the service, we'll give you a free month, or we'll, give you some kind of a discount or some kind of an extra perk. We'll make your service a bit better. Through those incentives, let's say your phone operators can convince half of those people that you've identified who are going to leave to stay. And so if you've got each customer, you measure each customer what they're worth to your business. Let's say they're worth $500, just as an example. And so the total revenue you're gaining from this targeting strategy is 500 times 2,000 is $1 million, right? So if you can increase the precision to 60%, remember right now, if you under that second bullet, your precision is 40%. If you increase the precision to 60%, then you're making half again that revenue, right? You're identifying half again as many people who are leaving. Your operators still have the same effectiveness. And so you're making $5,000 or $500 times 3,000 people, you're making $1.5 million. So you've got kind of a target in mind, which is, this isn't machine learning specific, but it's something crucial to being effective with machine learning. Is you think about the problem first, you think about what am I trying to do here? And in this case, you're trying to increase the precision of this targeting strategy. You have an existing strategy, it's making you X money. If you can increase the precision by some amount, you'll be making some amount more money. So it's crucial to have those things in mind, because then you can get in your head an idea of whether or not it's worth it to go through a project, for example, to deploy a machine learning solution. You want to put your effort where you're actually going to make money with that effort. And so now let's think a little more in detail about how we can use machine learning to increase the precision of that targeting strategy. So the important thing you need to do machine learning is the data, right? And so we're going to assume for this problem that you have this data. You have a customer, you've been tracking these customer outcomes for months. You know who's going to leave the service and who's not, or you know who has left the service and who hasn't left the service at the end of any given month. And also, a number of relevant attributes for each of those customers. So here in this kind of sample toy data set in this table, we have the number of minutes they've used on their cell phone service. We have the size of the bill that they were given last month. We have the number of times they've called support, and we have the number of times they visited the company website. And then finally, at the end here, this last attribute, churn, is whether or not they left the service. So this is kind of a pattern you're going to see in machine learning data, is there's going to be a bunch of attributes that we think are relevant for the prediction problem that we have, and then the result of the correct answer for the prediction itself. So for customers, obviously, in months that have already happened, you know whether or not they left. And that's key here, because here, if you had this customer now and you had to predict it, you would know how many minutes they used, you would know how big their last month's bill was, number of times they've called support, the number of times they visited the website, and you would have to predict this. But with machine learning, what we need to start with is a bunch of data that already has the right answer. And so that's what we have here, is data we've collected in the past. We know whether or not the customer left. And so for these customers, we know the right answer to our prediction problem. And so now what happens, right? You have all this data. You have a prediction problem in mind. You know how you need to perform on that prediction problem to make some money. And so, ta-da, machine learning, right? What happens? And so the idea here is we're going to use the data itself to create a better targeting strategy. And because we have the data, we really don't need to do anything else. That's the promise of machine learning. You don't need to, hire an analyst or wrangle one of your data guys to actually look at this data and figure out rules. You're going to use machine learning to do that for you. And then finally, we're also going to use the data to evaluate the strategy. So not only can we use the data to build the strategy that tells us, hey, this is how you can target more effectively, we're going to use that self-same data to prove to ourselves that the strategy works properly. Okay, so before we go too much further with that problem, let's make the discussion a bit more general. So what did we do to get together the data for that problem? What did we do when we wanted to apply machine learning to that problem? We're not there yet, but we basically got everything in place for our churn problem to do effective machine learning with that data. So how did we do that? Basically, we collected row column data about the problem as it was in the past. So we collected data from previous months where customers had churned in the past. Again, we have the right answer in that data. And so our machine, our computers, our algorithms can learn from that data how to make that prediction. So we're going to collect that data in row column format. Again, each row is going to be something you're trying to make a prediction on, and each of those columns is some information relevant to that prediction. And then you feed this data to a machine learning algorithm, and the algorithm itself will take this data and create a program, or if you want, a predictive model or a classifier. All these are kind of equivalent names for the same thing. And it's going to make predictions not just on the data that you fed it, but it also is able to make predictions on data in the future. So that's kind of the upshot, the coup de grace, if you want, is that the data or the model that you train on this past data is going to be general enough so that you can use it to predict the class of people, to predict whether or not somebody's going to churn in the future. You don't have to know the right answer. The model is going to tell you what it thinks the right answer is based on that past data. And so this breaks kind of a paradigm that we've always had in software engineering. So in traditional software engineering, you have two people. You have the expert and the programmer, right? And they both bring some sort of knowledge to the table. The expert knows how to make a prediction. So for example, in this case, there might be a customer data person, somebody who's had a lot of experience with customers, and they would know when somebody is going to churn. They would have information from their business unit that says, oh, when somebody calls support so many times and then they visit the website so many times, that means they're going to leave the service. So you have an expert about the data. You have somebody who knows things about the data. And then programmers in the traditional software engineering paradigm, the programmers know how to translate the expert's knowledge into computer code. So you pair that expert with a programmer who actually writes a program that codifies that expert's knowledge into something that you can run on data in the future. And so constructing a system requires both of these people, right? They might be the same person. It might be the same person who has expert knowledge about the data and also the ability to program, but you need both of these people. You need somebody who has knowledge about the problem, somebody who knows how to solve the problem that you want to solve, and you need somebody who can write that into a computer program so that that person's knowledge can execute quickly, essentially. And so the way that machine learning breaks this traditional paradigm is instead of an expert, now we're going to have data, and instead of a programmer, now we're going to have this machine learning algorithm. So with machine learning, data replaces the expert. This has a number of advantages. First of all, it's often more accurate than expertise. So when you measure this in an objective way, you find that people who are experts about the data often have wrong ideas about what the data itself is saying. So if you're using the data directly as your expert, you don't have that disconnect between what the data is saying and the data itself. Secondly, it requires no human expertise except collecting the data. So being an expert about whether or not some customers can leave the service is difficult, right? You have to have had experience with lots of customers. You probably have to talk to a lot of customer support people. Collecting the data is a lot easier of a thing to do. It's kind of a minor technical challenge compared to a large intellectual challenge, right? All you have to do is collect the data, you put it into a database, and you're done. You don't have to do the tricky intellectual work of trying to find rules that make proper predictions on this data. And then the third thing is that you might not even have that challenge, because chances are, for a lot of problems, the data is already just sitting out there. So you don't even have to really collect it. You just have to get it into reasonable shape so that you can do machine learning on it. And then the second part of this paradigm shift is that algorithms are going to replace programmers, right? So this also has a number of advantages. First of all, an algorithm is faster than a programmer, and that enables you to iterate. So for example, if you have some data, you want a programmer to write a program based on that data. That takes a while. If your data changes, your programmer has to update the program. Again, this is a person writing code, so it takes a while. If you're using a machine learning algorithm, this happens, depending on how much data you have, near instantaneously, right? You get new data, you get a lot more data, you get different data. You can put it through the machine learning algorithm, and you can get an answer back in minutes instead of days. So you can feel free to iterate over and over again, use more data, use different data, see how your model changes, and all that can happen very quickly in a way that it can't when you've got a human programmer creating your predictor or your classifier. Second, algorithms are more modular than programmers, right? So if you have a programmer and he's doing work for you, and you want a better programmer, or you hire a better programmer, it takes a while to insert that guy into your development pipeline. It takes a while to take a person and train them to properly code for you, even if they're very good at it, than it does to swap algorithms. The machine learning algorithms are fairly modular. They basically take input data and make a prediction, so you can swap one for the other. If someone discovers a great new algorithm tomorrow, you can put that algorithm into your pipeline with virtually no training at all, right? All you need is a proper implementation of the algorithm. You already have the data. The integration is already done for you. And then finally, data offers you the opportunity for performance measurement. So with expert and programmer, you kind of have to take it on faith that your thing works, right? The expert comes, he talks to the programmer takes the expert knowledge, he builds something, and they say, okay, here's the thing that we built. And really the only way to get an objective test of it is to take it out into the field and try it, which can be expensive in itself. But if you're collecting data, you can use that data to measure the quality of your system. And of course, if you're very good at this, you're already doing this, right? If you're concerned about the quality of your system, you're doing it anyway. You're collecting this data and you're using it to measure performance. So if you're somebody who's concerned about performance, if you're somebody who's concerned about, making sure your answer is honestly a good answer, then using data to measure the performance of the system is a lot more satisfying than having to either take it out in the field and collect that data yourself, or just taking someone's word for it.
Charlie? Hi.
Yes.
Yeah, before we proceed, we do have one question from Manfred Moorman. And then he's asking, is there an expertise required which data to collect?
Yeah. So I did I glossed over that a little bit, right? I said that collecting the data is a lot easier than having expertise about the data, right? I am minimizing the difficulty of collecting data to do machine learning. The nice thing about collecting data to do machine learning, it does require you to develop some facility with the data, some facility with machine learning. So you do have to have this kind of, what do you want? you have to have a different sort of expertise to collect data for machine learning. However, once you've learned how to collect data for machine learning and how to properly frame the problem, you only have to learn that one time, and you can apply that to a whole bunch of different problems. So once you know how to collect data for machine learning, you're kind of done. Whereas if you're collecting data for a specific problem and trying to learn about that data, you have to do that every time you're presented with a new problem. So machine learning is kind of more convenient in that way, is that once you've developed the expertise to do machine learning, it applies to a whole bunch of different data domains. Okay, so thanks for that question. That was a good question, and yeah, I did tend to I did minimize a bit the difficulty of collecting data for machine learning. And in fact, one of the lectures we'll do later on is sort of all about that, doing data transformations for machine learning, making sure your machine learning data is properly is properly scoped and framed so that you can do machine learning with ease on the data and with some success. So we will get to that in more detail. So right now, so on that subject, actually, let's talk a little bit about what it takes to create a program from data. So we've been a little bit wishy-washy up until now about exactly what we mean by create a program from data. So you're going to collect this data, you're going to plow it into a machine learning algorithm. How does that work exactly? So in the simplest cases, machine learning starts with this row column data. As I said here, each row, well, yeah, that's in the next slides here. So you have data that's rows and columns, data spreadsheet data essentially, or CSV data. This is the sort of data that machine learning typically works on. And so each row in the data is going to be what we call an instance in BigML. And an instance is something that the prediction you're trying to make is about. So each row in the data is something that you're going to try to make a prediction about. In customer churn, each row is going to be a customer, right? You're trying to make, each row is going to be a customer in each month. So each month you want to make a prediction about each of your customers. So you need a row in your data set for each customer each month, right? Similarly, this kind of generalizes to a whole bunch of different domains. In medical diagnosis, each row is a patient, right? You want to make a prediction about whether or not a patient has some disease. So each row is going to be a patient that may or may not have that disease. For fraud transaction, when you're doing fraud transaction with credit cards, each row is going to be a transaction that you're trying to decide whether or not that transaction is fraudulent. And if you're working in the financial markets, for example, each row is going to be a day. If you're trying to forecast the closing price for a given day in the market, each row has to be a day where the market closed. And then the columns in the data set are going to be information that help us make the prediction. So in churn prediction, we saw the columns in the data set are going to be the minutes that you used on your cell phone plan or the number of times you called support. For medical diagnosis, it's going to be the results of some physiological tests that determine whether or not you have a disease, like your body weight or your body temperature, or the results of various tests that the doctor may have ordered. For credit card fraud transaction, you want information about the transaction, such as the amount, the location, the name of the business, so on and so forth. Maybe you want the geographical distance from previous transactions. That could be relevant. And then for the market closing price forecast, you probably want to know the opening price. You want to know the previous day's opening close. Maybe you want to know the trend from the last 5 days. These are all going to be columns in your data set. And then immediately, if you're thinking about machine learning, the next question that somebody's going to ask is, well, what kind of information should I collect, right? If I have the customer churn problem, for example, I could collect any number of columns about that particular customer. Maybe I know their age, or maybe I know where they live, or maybe I know how long they've been with the service. Is any of that information relevant? How much information do I need to collect to do good machine learning? Unfortunately, there's no pat answer to that question. It's domain specific. It depends on, first of all, the quality of information that you can collect, and second of all, how easy your problem is. But there are a couple of questions you want to ask before you start to collect more information. First of all, how much does it matter? How much do you think that getting this information is going to affect the accuracy of the prediction you're trying to make? If it's something that's very, very informative for that prediction, then of course you want that. If it's something you only think might be informative, then maybe you can do without it. But this is where you, as the domain expert, the person using machine learning, get to apply their knowledge, right? You get to decide what information is going to be relevant to this prediction. And then the other side of that coin is, how much does it cost? If we're talking about medical diagnosis and you say, oh, I could really diagnose this accurately if only I had an MRI from this person. It costs a lot of money to give every patient an MRI, whether they have the disease or not. And so typically, that's the other factor that you're considering here. Even if it is very valuable information, if it costs thousands of dollars per row to collect that information, then you probably want to, you may not want to collect that information in any case. And then finally, one of these columns, so you've got these rows, you're trying to make a prediction about each row. You've got the columns, which are information about each row. One of these columns is going to be special, right? One of these columns is going to be the objective, which is the thing that we're trying to predict. So for the churn prediction, one of the columns is going to contain the information about the customer. Did they leave the service or didn't they? For the medical diagnosis domain, one of those columns is going to contain positive or negative for the disease that you're trying to predict. Credit card fraud transaction, one of the columns is going to contain, is this transaction fraudulent or isn't it? And for the market closing price forecast, one of the columns is going to contain the true closing price for that day. And remember here, the goal with this data, so you've got your row column data, you've got one field, that's the field you're trying to predict, one column that contains the information that you're trying to predict, and we're going to give this to a machine learning algorithm, and the output of the machine learning algorithm is going to be this program, which is often called a model or a classifier or a predictor. And basically the inputs to that program are going to be a single row of data, excluding the objective field. So you're going to feed it everything that you know about that row that you're trying to make a prediction about. And the output of the program that the algorithm has constructed is going to be a prediction of the objective for that row. So this is kind of important, right? At training time, when you're collecting the data for training, you know the objective. One of the columns in your data set is the value for that objective. At performance time, at prediction time, when you're actually using the model that's trained, you don't know that information. You're trying to predict it. And so the inputs are all of the information from that training data, except that one column that you're trying to predict. And the output is the prediction for that column. And perhaps the most important thing about all this is that the input row doesn't need to come from the training data, right? If this were a predictor, if you trained a predictor that could only make predictions about the training data that it had already seen, it wouldn't be very interesting. It wouldn't be very useful. The power of the predictor is that it can make predictions, make accurate predictions on input rows, on input data that it didn't see in training, input data that it may see in the future. So let's talk a little bit about when this is a good idea. So machine learning, it's really exciting, right? Like when you take your first, when you're in computer science, you're in your undergraduate degree, you're taking classes. When you're maybe a junior or a senior, you take your first machine learning class. Like, wow, I can write a program just using data that I have. That's so exciting. You know, it's so much work to write a computer program. This is so much easier. And so let's temper that excitement a little bit with some realism here. Remember, using machine learning means replacing an expert and a programmer with data and an algorithm, right? So what you want to find when you want to deploy a machine learning solution is a place where the expert and programmer are already an appropriate solution. And then you want to find, in particular cases, where it's difficult to find an expert and programmer for whatever reason to do this work. So if it's hard to find an expert, that might be a good place for machine learning. Can the programmer encode the expert's knowledge quickly and accurately enough? If it can't, if a programmer is unable to do that, then that might be a good place to use machine learning. And so there's kind of general guidelines, a few general guidelines in place about identifying situations when this is a good idea. So one important case here is that the case where people can't tell you how they do it. So if you're reading, for example, if you're reading text from a page, this is easy. Almost any adult can read text on a page. For computers, this is a very difficult problem without machine learning. And it's specific. It's not because there's a lack of experts. We're all kind of experts at this problem. It's because an expert can't explain to a programmer how they do this, right? And so it's difficult for a programmer to write a program that does this without machine learning. So good examples here are usually problems where humans are taking sensory input, like optical character recognition, again, reading text on a page, object detection, so looking at an image and saying, oh, there's a truck and there's a tree and there's a horse. This is something that's very difficult to do without machine learning. Speech recognition is near impossible without machine learning. So these are examples of problems where anybody could do it, but they have trouble saying exactly how they do it. Another important case is where humans are rare or expensive. So if you've got the medical diagnosis domain, for example, you need a doctor to read your MRI or to look for any sort of bioabnormality. Doctors, as a percentage of the population, are fairly rare, and so this might be a good place to deploy machine learning. Some people in the past have trained algorithms that will autonomously pilot helicopters, right? And this is also a difficult problem because not too many people are fantastic at piloting a helicopter. So this is a great place where you can deploy machine learning. Machine learning learns how to drive the helicopter. You no longer need a helicopter flying expert. And then finally, game playing at high levels. So you've seen machine learning, probably you've seen in the news that machine learning has had a lot of success playing games like chess and Go, these elaborate strategy games. At very high levels, there aren't too many experts who can play at those very, very high levels. And so it's good to have a computer who's up there able to play at those high levels. This is a place where we can use machine learning to train kind of a superhuman Go player, because it's unlikely that a very good Go player would be able to would have the time or inclination to collaborate with the programmer to encode the Go strategy at the resolution it's needed to play very well. So machine learning, of course, can do this automatically. And then a different sort of case here is the case where everyone needs their own algorithm. So there are a lot of cases like, for example, spam detection in your email box. You yourself, the email user, are getting a specific distribution of spam messages. And so we need a machine learning classifier or a machine learning model for every person who uses the service, because for every person, they're getting a different sort of spam and they're getting a different sort of legitimate email traffic. And so telling the difference between those two is different for every person. And of course, there's no opportunity for a programmer to go into every person's email account and write a specific program for every single person that tells the difference between spam and not spam email. This is kind of tailor-made for machine learning, because machine learning models can go into every account, draw a nice boundary between spam and not spam, and move on to the next account. And if you have millions of users, this is the only solution that can do this quickly enough to be effective. And there are several other problems that are of the same type. So activity recognition, for example, if you've got your cell phone and you're trying to figure out what the person is doing, walking or running or driving based on the accelerometer and gyroscope data from their cell phone, this is an example, again, where everybody needs their own model to correctly determine that. What the accelerometer does when everyone walks is going to be different. It's going to be different for men, for women, for tall people, for short people. And so you need a specific classifier. It's almost fingerprint-like for every single person who you want to have an accurate prediction of what they're doing. Location prediction is another one. So if you're sitting somewhere and we want to have an idea about where you might go next, because maybe we want to predict traffic on the route that you're going to take or something like this. This is something, again, where the machine learning model needs to be different for every person. So for example, if a person is sitting at work, probably the next place they're going to go after that is home. But home, of course, is different for every person, and work is different for every person. So you need a different machine learning model to make that prediction for each and every person. And of course, home and work is kind of a trivial example, but it might be that a certain person, on Saturdays goes to yoga class, and they go to yoga class on Saturdays every day at the same time. And so you would need a specific machine learning model to make those sorts of predictions. And then in general, anything that you want to personalize. So anything where you want to make any sort of personalized prediction based on that person's data stream, that requires machine learning. Now that everybody has a mobile phone, obviously everybody's generating a stream of data. And so prediction problems like this can be kind of whatever you want based on that mobile phone data. And as we get into sort of the world of the Internet of Things, that has the potential to be a big deal in the machine learning world as well, because if your refrigerator, for example, is generating a stream of data, then you can make predictions from that stream of data. And the same with any appliance in your home. And then the last case I'm going to talk about here where you might want to use machine learning is the case where every little bit of performance counts. So in the markets, I worked in the financial markets for 2 or 3 years, and that was a case where just 1% accuracy could make you, thousands of dollars in the aggregate. And so a lot of times there are a lot of problems in which humans can get, just by hand, can make a solution that's 80 or 90% accurate, let's say. And getting that last 20 or 10% accuracy is very, very difficult for a human to do, because they have to fiddle with various parameters of whatever problem they're looking at. This was the case in the markets, right? A human operator could buy and sell equities or debt in a way that would make him some money. But if you had a computer doing that same thing, you could make a bit more just because it had, all that data to work with, and it could do better. It could do slightly better than the human performance using classifiers built on all that data. So if that's what matters, if you find that the difference between 85% accuracy and 90% accuracy is a big deal, there are a lot of machine learning applications where you can get performance that's slightly superhuman. And if it's a big deal in that domain, then you can get it using machine learning. Another example here is handwriting detection. So if you've got a prediction problem where it's easy, where any human could do it, then the penalty for making a mistake is fairly high, because if you show that to a user, if you recognize the letters in their handwriting incorrectly, then a user is going to think, oh, this is a terrible system, it doesn't work. I'm not going to use this thing anymore. So the penalty for getting an easy problem wrong can sometimes be very high. And so you might want to use a machine to learn a classifier rather than rely on a person to write a program that might be more error prone. Basically, anytime there's a performance critical system that's been hand built that could be rebuilt using data, you might want to think about that as a case where you could deploy machine learning. Again, machine learning has the ability to optimize every little bit of performance out of a situation where humans, can do very well, can get 80 or 90% performance out of a situation. And if it matters, if that last little bit of accuracy matters, then machine learning might be right solution for that domain. But again, this is a place where I'd counsel not being too myopic about that last little bit of performance. So there's a lot of cases where people expect a huge, like, so again, when I was working in the markets, for example, there are some people who would say, oh, you know, our trader is making this amount of money. If we deploy machine learning, we're going to make 2 or 3 times that amount of money. That's not the case in a lot of domains. In a lot of domains, if you already have a hand-built system, if you already have a human doing the task who's very good at it, then deploying machine learning to do the same thing might only get you, you know, a 10% increase in performance or a 20% increase in performance. And maybe that's a big deal in your domain, but maybe it's not. And so this is where that first slide where I had begin with the end in mind, where you should know how much, you should honestly have an idea of how much you can improve the state of the art, whatever the existing structure happens to be. You should have a good idea about how much machine learning is going to improve that and how much money you can make before you go on this path of trying to provide a machine learning solution. And so here's the other side of the coin. When is it a bad idea? So I just talked about 4 or 5 reasons, 4 or 5 cases there where it's a good idea to use machine learning. And of course, there's just as many, if not more, cases when it's not a great idea to employ machine learning. One is where human experts are cheap and easy to come by. So for example, again, I'll take another example from the markets. When I was working there, we tried to develop a system where you were going to use natural language processing to read the news as it came in very quickly and to suggest actions based on that news. So if bad news from some country came in, you would want to divest yourselves of all the equities from that country, for example. It turned out that there was no benefit to doing this because our traders could just read the news as it came in, and they could make themselves they could make for themselves these simple rules about what they wanted to do based on the news. So this is something you could solve with machine learning if you really wanted to. There's just no good reason to do it. Another example of this, I used to work at a company that made very large industrial printers, and they wanted a machine learning system that would look at images from the printer, and they would decide whether or not the printer was defective based on taking you know, a quick picture of what was coming off of the press. And the reason that this was useful is because the press was running at, you know, many hundreds of feet of paper per minute, and so you could save like a mile or 2 of paper if you could detect that defect in the image automatically. You could save a lot of wasted paper. It turned out that this was not a good idea because a human operator would every once in a while look at the paper coming off of the press. If they saw a defect in the image, they would stop the press and correct the defect. And yes, it would waste like 10 miles of paper because the human wouldn't look that often, but it turns out that 10 miles of paper did not cost very much money. And so this was another place where, yes, you could solve this problem with machine learning, but again, if you did, it was only going to make you, you know, a few dollars every day based on this wasted paper. So this was a problem where you, again, did not need machine learning. You already had a good enough solution in place. A third case is where a program is easily written by hand. So if you don't have a solution in place, but you could have a programmer do it with very little trouble, then of course you don't need machine learning to write this program for you. If it's a program that can be solved with a few simple if-then rules, you don't need to use machine learning. The solution is easy enough to encode, easy enough for a person to encode that it's not a big problem. And of course, if there's already a hand-built program in place to do something, then you might not need machine learning because the program you already have there costs $0 to develop because it's already there. And so it might be good enough. And then finally, the last case is where the data is difficult or expensive to acquire. So even if a machine learning solution would be a great fit for a given problem, you need the data to actually build the solution. So a good example here is medical domains, where we could do a whole bunch of things in medicine if only we had the data. But of course, it's very difficult to get medical data, right? There's confidentiality issues. It's spread across a lot of hospitals. It's in a lot of different formats. if the data were centralized and easily available and no one was concerned about their privacy, then this would be a domain where we could develop a lot of great technology, but that's not the case. And so machine learning is slow in this domain. There aren't a lot of places where we can apply it yet. People are getting better about this, and people are getting more able to deal with sensitive data, and so that's changing. But right now, it's still very difficult to get good medical data. Another example of this where the data is difficult to acquire is automatic processing of images. Up until recently, this was a problem that was very difficult, where we had a lot of images online. There are a lot of pictures on the internet, but we don't have data about what's in those pictures or what those pictures are of, for example. And so you need human annotators to go through every single image and tell the machine, hey, this is a horse and this is a tree and this is a car. That's a huge effort to label all of those images if you want to create a classifier that can label them for you. This is basically taken care of now. Various people have been very clever about collecting this image data, and now we're able to annotate images on the internet without too much problem. But this was a huge effort by Google and some other people to get labels for all these images to create a good training set for these image classifiers. It was an effort that took years. I remember going to conferences for several years in a row, and they were talking about, how do we get all these labels? And finally, after years, they did, but it was a big effort. Okay, so we've talked about what machine learning data looks like in general. We've talked about when it's a good idea to use machine learning. So let's actually go and start to talk about what machine learning looks like in the real world. So I've said up until now that machine learning algorithms create a computer program. That isn't completely accurate. The more accurate statement here is that they search for a program that's consistent with the training data. The search for a program that the machine learning algorithm does, it has to be very clever because it's searching in a space of thousands of possible programs. And usually to help the search along, there's some sort of Occam's razor involved. So it's looking for the simplest explanation of the data that it can find. And the space of possible solutions in which the algorithm is operating is called its hypothesis space. And so you might know the word hypothesis if you've taken some kind of rudimentary science classes. The word hypothesis is an idea that you have that can be confirmed or refuted by the data. And so the algorithm is sort of doing the same thing a scientist does, but in reverse. Remember, in the scientific method, again, from your high school science class, what you do is you make a hypothesis, you have some idea about the world, and then you collect data that either confirms or refutes that hypothesis, and then you have a conclusion. You say, yes, my hypothesis was confirmed, or no, my hypothesis turned out to be wrong. The algorithm does this in reverse. The algorithm first takes the data, and then it makes a whole bunch of hypotheses about the data, and then it looks at the data to see which of those hypotheses is being confirmed by the data, and it selects that as your machine learning model. So this modeling process is a lot like doing science in reverse of the way we're used to. And so I'm not going to go through it. I want to get to all the slides, so I'm not going to go through this in too much detail. But depending on the sort of model that you're creating, if you're creating a logistic regression or a neural network or a support vector machine, these are all types of machine learning models. They all have different hypothesis spaces. And this is what makes machine learning algorithms different from one another, is the hypothesis spaces they're operating in, the sorts of hypotheses that they're considering. And so let's think about this more concretely. Let's think about this toy data set that we have. And let's think about a simple hypothesis space. So our hypothesis space in this example is going to be, I'm going to choose a threshold for some attribute, and I'm going to predict everything above that threshold as being the majority class of the things that are above that threshold. And I'm going to predict everything below that threshold as being the majority class of all the things that are below the threshold. So what do I mean here? So here's a basic threshold model, right? Here's a very simple hypothesis about this data. I'm going to say that everybody who visits the website more than 0 times has one class, and everybody who visits the website less than 0 times, or 0 times exactly, has a different class. And so you can see I've highlighted the people here who visited the website more than 0 times. You can see that 3 of them do not churn from the service, and 1 of them does. And so for this, I would predict no. The majority class of these people is no, right? 3 out of 4 of them do not leave the service. So I'm going to predict no for that subset of people. And for the other subset, for the people who don't visit the website at all, we again have 3 people who are labeled no, that they're not going to churn. And we have 1 person who's labeled yes, that they are going to churn. And so the majority class is again no, so I'm going to predict no. And so this is kind of a weak threshold, right? Weak in the sense that if I split the data into 2 subsets based on this threshold, I get the same prediction either way. The majority class of both of those subsets is the same. And so it's not a very good predictor, right? It's always going to predict that the person's not going to churn. That's not very interesting. So here's another one. Let's say I'm gonna create this threshold based on if a person used their cell phone, used more than 200 cell phone minutes. And so I've got those people highlighted, the people who have used more than 200 cell phone minutes. And for 3 of those people, again, they don't leave the service, and 1 does. And so I would predict no overall for this subset. And then similarly, the people who aren't highlighted, again, 3 of them leave the service, or 3 of them don't leave the service, and 1 does. And so I'm going to predict no again for that subset. So this would also be a bad predictor, right? It would predict no all the time. But now let's take this threshold here. Let's take if their last bill is greater than $180. In this case, the people who are highlighted, 2 out of 3 of them are yes. And so I would predict yes for that subset, and I would get 2 out of 3 of them right if I made that prediction, right? And similarly, for the people who are not highlighted, all of them are no. And so if I predict no for that subset, I get all of those people right. So this is kind of a nice threshold, right? Instead of, it predicts yes for some people, it predicts no for some people, and it gets only 1 of these examples in the training data wrong. So this is a good outcome. This is a better outcome than these previous 2 thresholds where I was going to get 2 examples wrong based on my predictions, right? Because 3 out of 4 of these people were no, 3 out of 4 of these people were no. And so I would always get that 4th person wrong. Here, I'm only getting this 1 person wrong who happened to have a huge bill and stayed with the service anyway. So this threshold is good. There's something good about this threshold. And what we like about this threshold is the subset purity. So if it splits this data into 2 subsets where the value for churn is uniform across the 2 subsets that it's split into, which is nearly the case here, right? Again, all of the people who are not highlighted are no. That subset is pure. The target variable, the objective variable, is the same for all of those people. And then among the highlighted people, it's nearly pure. 2 out of 3 of them are yes, so that's still pretty good. So that's how we know that we've asked a good question about the data, that we've set a good threshold on the data. And so how do we find the best threshold? Again, here we've taken these 3 sample thresholds, and oh, here we found a good one. So in general, how do we find the best threshold to set? Well, we could just try them all, right? We could try every possible variable and every possible value for that variable and just check to see how pure the subsets are that we split the data points into. And so now we have this kind of good question. This is a pretty good model, right? This could be our machine learning model. We could say if the person's last bill was greater than $180, we're going to say they are going to leave the service. And if the last bill was less than or equal to $180, we'll say no, they're not going to leave the service. And according to our training data right here in front of us, that would do a pretty good job, right? That would predict 7 out of 8 of these people with the correct churn value. And not only that, but it would catch all of the people who churn. It would introduce 1 false positive, but everybody else who it predicts is going to churn is actually going to leave the service. So this is a pretty good little model. if we wanted to make it better, remember we do have this one person that we're predicting incorrectly here, the person with the $305 bill who stays with the service anyway. We're predicting they are going to leave the service, and then they don't. And so to mitigate this, we don't need to stop at just one of these thresholds. We could introduce another one. Let's pick out the people from that threshold who have had more than 0 support calls. And so you can see our guy who has the $300 bill, he never called support, right? And so this excludes him. It pulls in the other 2 people. And so we have a nice satisfying outcome here, right? The people whose last bill was greater than $180 and they made a call to support, those people we label yes, everybody else we label no. And that's our model, and it classifies all of these people perfectly.
Charles, just one comment before you proceed with the next slide. Yes, we do have a question from Wolfgang Fleischer, and he asks, can data sets be as small as this one in order for the algorithm to identify a solution, or do you need usually many more data sets?
Yeah, so this is absolutely the right question to be asking at this point. So the answer to that question probably isn't as satisfying as you're thinking. Basically, it depends on 3 things, right? So the amount of data you need depends on the accuracy of the classifier that you want, the difficulty of your problem, and the complexity of the model that you want to fit. And so this is kind of advanced material in the machine learning world. But essentially, just to make it as simple as possible, if you have a tough problem, if it's difficult to select these subsets of people here, then you need more data to learn a correct classifier for that problem. So basically, the harder the problem is, the more data you need. So it's possible that you get a really easy problem and you only need a few data points to create a perfect classifier. Typically, if that's the case, a human can usually construct a good solution by hand also, if the problem is that easy. It's the cases where you don't have a really easy problem, you can't learn it in just a couple thresholds here. Those are the cases where you really need machine learning, and typically those are the cases where you need more data. As a rule of thumb, I typically don't see too many useful models until I have data that numbers in like the middle hundreds of instances. So 200, 300, 400 instances, that's where you start to get models that are not trivial, that are not easily constructed by people. I have had problems where you have less data than that, but they're pretty rare. When you get into the hundreds of points, you can kind of start to construct models that are non-trivial. And then some problems like the image recognition problem that I was talking about before, where you're trying to identify a tree or a horse or a car. So those problems, image data is so dense and so complex that you really can't do a good job unless you have tens of thousands or hundreds of thousands of points of training instances to train that model on. So again, like it's possible that you create a good model with just a few dozen points. But for serious models, that are actual real machine learning solutions, in general, you would like to see at least somewhere in the mid hundreds of points or more before you start modeling. The other caveat there is that sometimes that's just the data you have. The data you have happens to be just a few dozen points, and it's not the case that you can't do anything at all useful with that data. You still might be able to get a model that's kind of good enough to work with that data, or you might just model the data to look at the model and see what the model looks like, and that might give you more information about the data. You might just be exploring the data. So it's not that you can't use machine learning on the data if you just have a few dozen points. It's that the accuracy of your classifier is likely to be lower than you want if you only have a few dozen points. So that was kind of a long-winded answer, but the short version is that if you want a more accurate classifier, you have a complex problem, that's when you need more data. And again, hundreds of points is sort of a good starting point to think about when you have enough data. And we'll see a model trained on real data, what that looks like in a few minutes here. And this is the sort of model we're going to see, and the sort of model we just kind of built by hand there is the decision tree. So there's no reason we have to stop at 2 questions here either. Here we have the one threshold, the one question we're asking about the data, is their bill greater than $180? And then this other question is, have they called support more than 0 times? So it's a decision tree here, right? If their last bill at the top there, it's kind of a flow chart. If you go into the top node, it asks a question about their last bill. Is it greater than or less than or equal $180? If it is, you go one way down the flow chart. If it isn't, you go the other way down the flow chart. If it's less than $180, we just predict no. If it's greater than $180, we ask about the number of times they've called support. If that's less than or equal to 0, we predict no. And if that's greater than 0, we predict yes. So you've got this kind of flowchart style diagram that we've constructed automatically based on the data. And so this is exactly what we show you when you create one of your default, the default machine learning model in the BigML interface. Each node, each of these little circles in the model represents a question you're asking about the data, and the branches leading from either side of that circle are answers to that question. So if you take one branch, it means you're making one answer about that question. If you take the other branch, you're having the different answer about that question. The thickness of the branches show how much training data went down either path. So if in this case, it looks like on the left branch coming out from the top node here, a lot of the training data took this path and very little of the training data took this other path. So that might be interesting information to you, how many people go to one side of this threshold and how many people go to the other. And then when you get to the leaf node or the terminal node at the bottom here, you decide on the prediction. And usually you decide that it's the majority class for the subset of the training data that makes it down to that leaf, that takes that path through this flow chart. And then the last thing our algorithm kind of has to decide is when to stop. We don't need to go into too much detail here because this is kind of a detail of the algorithm, but basically it's going to stop when it's classified every point perfectly. That's the main stopping criteria for these threshold-based models, these decision trees. So you're going to split the data and split the data and split the data until every single point is classified perfectly by the node that it's in. And then, of course, to do a prediction, all you have to do is put a point through the little flowchart, right? You test all of the different thresholds, you follow it from branch to branch, all the way down to the bottom. And then once you're at one of those bottom leaves, one of those terminal nodes, you can make a prediction about that point. And so now kind of what you've been waiting for is the BigML interface. Let's actually do some machine learning with BigML. And so supervised learning with BigML typically proceeds kind of stepwise. First, you have a data source where you upload the raw data, your raw data to the platform. And next you have a data set, which is BigML takes a look at your uploaded data, summarizes it, puts it into the platform in kind of a standard format so it can do all other steps quickly. And it also gives you some interesting information about each column in the data set. And then from that data set, you can create a model. There's a default model, which is a single decision tree, but there are also many other types of models that you can create that we'll talk a little bit about here as we go forward in the training sessions. And then finally, you can use that model to either make predictions or you can evaluate that model using some training data. And so basically, if we're making a prediction, again, we're sending a point through that little flow chart. We're sending a data instance through that flow chart and making a prediction about it. If we're doing evaluation, we're making a bunch of predictions and measuring their quality. So how many of those predictions did I get right? Moving through each step in that process typically creates a resource. so when you create a data source, that's a resource. It's a thing in the BigML platform. It's a thing that has an ID that you can always return to unless you delete it. And then when you create a data set from the source, that's another resource in the BigML platform. That's another thing that has a unique ID. Models all have unique IDs. Evaluations have unique IDs. And the nice part about these things is that the resources in the BigML platform are immutable. So you can't, you can delete them, but you can never change them. So no matter what you do in the platform, resources that you've already created are always there, and you don't need to you don't need to worry about hurting them at all by doing different things with your data. And so let's go. Let's see, here we go. Yeah, so finally getting to the BigML platform here. Here's the here's your private deployment. I have an account on A1 Digital's private deployment, and here I'm going to delete this thing that I already created. But here's what you'll see when you first log into the platform is a list of data sources, a list of files of data that you've uploaded to the platform. And so if I look here I have this file churn CSV, and if I open this up in just a spreadsheet program, you can see that the data is exactly the same as what I was showing you before. I've got more of it. I've got a few hundred points, like I was telling Wolfgang earlier. I've got kind of a non-trivial amount of data here, but it's data of the same shape, right? I've got the minutes, I've got the amount of their last month's bill, the number of times they've called support, number of times they visited the corporate website, and then whether or not they left the service at the end of the month. So this is actual data that I have just sitting on my machine in this CSV file right here. And to upload it to the platform, all I have to do is drag it onto the BigML page there. It automatically uploads, and you see I've got that file sitting in the platform. And so what you're seeing right now is the list view. So for any of your resource types, sources, data sets, all your supervised model types, predictions, etc. For any type of resource, you can click on that and you can get a list of all of those resources that you've created in the platform. So here I'm seeing all the sources that I've created in the platform. I've just created this one called Churn CSV. And then in the resource view, you can view the resource, and you can also create other resources from that resource. Like, for example, if you, in the data set view, you can create a model from that data set. Up in the resource view, I've circled these two icons here, which are going to be very important throughout the rest of the trainings. This is the cloud action icon here that has a bunch of one-click actions, things you can do in one click. And then the gears icon here is the configuration icon that allows you to configure options for the one-click action. And we'll see what that means in a moment. So here's my list of sources. Like I was saying before, the next step after creating a source, creating a source is to create a data set from that source. So if I click on the source, you can see it identifies automatically the columns in that source, and it shows me some of the sample data from each of those columns. So I've transposed this data set. Each row here represents a column in my original data set, and it's just showing you that I've detected all of those columns properly. It also has a guess at the type of the column, and it's for this data set, it's getting all of them right. It's guessing that minutes used is a numeric type, and all of these other variables that I've passed into the model are all numeric types. And then churn is a categorical type. So churn isn't a number, it's a sequence of characters. It's the value yes or no. And so it's not a number, and so it's just a variable that can take a couple of different categories. So those are the two most common types of data that you'll encounter in machine learning, are the numeric type of data, which is just a number, and then the categorical type of data, which is a column that can be one of several categories. And so this is my source. I'm going to create a data set from that source. If I go over here to this cloud action menu, again, I can go to one-click data set. That's the easiest way to create a data set from that source, using all default options and not having to worry about configuration. And so you can see here now BigML has serialized all of the data from that data source. And it's also now giving me some information about each of the columns in the data. So for the minutes used, I've got a histogram of the values that you see in the data. So for example, there's 58 rows in the data that have a value for minutes used between 105 and 114. And you get this for all of the columns in the data. You get this little nice little histogram visualization of the values for that column. For support calls, you can see I only have a few. Most people never call support. Of the remaining people, some call once, some call twice, some call 3 times, but those are the only 4 values that I see for that column for support calls is 0, 1, 2, or 3. And then on the bottom here for the churn variable, you see I have 917 people who don't leave the service, and I have 82 people who do leave the service. So I've got an attrition rate, a churn rate of something like 8%, right, in this data set. Now, like I said, the Cloud Action menu, especially in the data set view, it's terribly useful. It allows you to create all of the things you can create from this data set. So there's a whole bunch of things I can do here. We're not going to talk about most of them today, but one of the things that it allows you to do is this one-click model, which means it's just going to create a decision tree from this model. It's going to assume that the last variable in my data set, this churn variable, is the objective, and in our case, it is the objective. And then it's going to try to create a model that predicts that churn variable from the other 4 variables, the other 4 columns that it sees in that data set. So let's do that. So I create a model. Creating a decision tree is not terribly expensive. It usually only takes a few seconds to get a decision tree out, a single tree. Other models are sometimes more expensive to create time-wise. They take a bit longer, but decision tree will usually take you something far less than a minute. And so here's the model that this thing is constructed. And you can see here's the top node, which says that total, I had 999 instances in my data. 917 of them were no, and 82 of them were yes, they did churn. And so that's what the class distribution of this data set looks like. And then the first question that we're going to ask here is how many times did they visit the website? How many times did this person did a person in the training data visit the company website? And if it was more than 3 times in this data, there were 22 people who visited more than 3 times, and they all churned. They all left the service, all 22 of them. You can see all 22 of them are yes. If they didn't, then over here, you see that of the 977 remaining instances, of the 977 who did not call the website more than 3 times, 917 of them did not leave the service, and 60 of them still left the service. And you can follow this all the way down, right? Here's the subset of people for whom they called the website. They did not call the website more than 3, or they did not visit the website more than 3 times, and also they did not call support more than twice, right? You can see the list of, if I hit shift here, you can see the list of questions that led to this particular node. And then here, if I go to the other side of that node, here's the people who didn't visit the website more than 3 times, but who called support more than twice. And I'm going to predict that they do, in fact, churn. And you can see 11 people meet those criteria, and 11 people have left the service. So this is the shape of the decision tree model. It splits your training data into these subsets. And when you get to these green nodes that have all of the same class, it decides to make a prediction based on that node. And now, of course, again, as I've been saying all along, the money here, the special part of machine learning is that you can use this model to make predictions on new data just by plowing them through this series of questions, right? And so if I go up here, here's the Cloud Action menu, and you can see I can do a number of things here. But one of the important things I can do, maybe the most important thing I can do, is predict. using this model. And so if I click on predict, you get this form where you can input all of the attributes for some customer, for some cell phone service customer. Here I'm going to say they didn't visit the website ever, but they called support 3 times. And so our model is going to predict churn is yes, and this is the confidence of that prediction is 74%. If I lower support calls all the way down to 0, they're going to predict churn is no, and they're a little more confident about that. And you can see as I change these variables, the prediction of the model will be different depending on the values for these variables. So basically, anytime I want to classify a new person, one way I can do it is I can put all their information into here, and that will give me the model's prediction. So that's the basic workflow, the basic machine learning workflow, without any of the bells and whistles that you're going to learn about later. Always machine learning kind of fits this this workflow, the sequence of steps where you upload your data, you create a model based on that data, and then you do something with that model. You make predictions, for example. Let's see. So when I was showing prediction confidence up there, I showed you in that prediction form that not only do you get the prediction for the model, but you also over here get some estimate of the model's confidence in that prediction. What exactly is that? So each of those terminal nodes is returning a prediction, but you can also say based on how much data made it that far in the model, how confident you are in the prediction. So the confidence you're seeing up there depends on 2 things. The number of instances that reach that terminal node. So if you get to a terminal node, if for example, a whole bunch of people meet the criteria that leads to that leaf node, then you're very confident in the prediction because you're making it based on a whole bunch of people. And then the other thing that's important in the prediction confidence is the purity of that leaf node. So if a whole bunch of people make it to some leaf node, based on the questions that are asked getting to that leaf node, if a whole bunch of your customers make it there and they're all exactly the same class, if none of them left at the end of the month, then the model's very confident in its prediction. If half of them left at the end of the month and half of them didn't, then the model is not very confident, right? It could go either way. It doesn't know. So you're kind of thinking of each little instance that makes it to each terminal node as a little expert. And so you've got 1,000 experts saying, oh, I'm going to leave the service. I'm not going to leave the service. I'm going to leave the service. I'm not going to leave the service. Based on the aggregate of all those expert opinions, you're either very confident or you're not confident in the prediction that's being made at that leaf node. So if there's one instance, for example, at a leaf node, and that happens in this model, if we go back to the model that we just created, we'll go supervised models. And here's the model that we just created moments ago, 6 minutes ago. So I'll click on it to get it back. And here it is. And as I said before, you have a unique ID for this model that will never change. It's up here in the address bar of your browser. This is the unique ID for this model. And if we go to one of the bottom leaf nodes, so here, here's a way of filtering nodes. We can say we only want to see the leaf nodes that predict yes for the churn variable. So I'm going to do that just because I want to see some of these yes nodes. And if we go all the way down to the bottom here, we see here's a leaf node that has a single instance in it, and that person did leave the service. And to get to that person, you had to ask all these questions, right? They visited the website this many times. Support was called this many times. You can see that a whole bunch of times they're asking questions about last month's bill. Was it greater than this? Was it less than this? They're identifying a little tiny range of last month's bill where this person only is present in that tiny range. So this isn't a terribly reliable prediction for reasons we'll get into in later sessions. This is kind of there's too many questions here to make this prediction reliable. And part of the reason that the prediction is unreliable is because there's only this one person who meets all those criteria. And so you're making a prediction just based on that one person. And so as you can see, the model is saying, well, yes, I do have this one person here, and yes, they did leave the service, but it was only one person, and so my confidence up here is very low, right? I only have a 20% confidence. Yes, I'm predicting yes, they will leave the service, but I'm predicting it based on not very much data. And so this is essentially what prediction confidence is it's tempering this prediction based on how much data you're making it on. You can see the converse up here is if I go way up to the top, now I have 22 instances. Now I'm a lot more confident. Yes, 22 people all left the service who visited the website more than 3 times. I'm pretty confident about that. So I'm going to say 85% because I have a lot of people here that I'm basing this on comparatively.
Charles?
Yes.
So we do have another question from Eric Auer, and he says, how can you handle such cases where you have correlation in data, but not causality?
Yeah, so it doesn't. This is a question that gets asked all the time. It's actually something that we've blogged about in the past. That's not what these models do. In general, machine learning doesn't know the difference between causality and correlation. All machine learning knows is correlation, right? And if the correlation happens to be causal or non-causal, that doesn't make any difference to the model. It's just trying to correlate the two variables. The causation and correlation relationship is something that you, as the modeler, have to handle before the data gets to the machine learning algorithm. So if you have a suspicion that, for example, something is correlated, but it's not causal, and you need the information that you're feeding to the model to be a causal relationship, you have to make that determination, and you have to either decide to feed that feature to the model or not. There are other sorts of analyses you can do that we do enable on the platform that help you determine whether or not a relationship is causal or not. But in the vanilla case, in the basic machine learning case, this is something that's left to the operator. And actually, maybe afterwards, I'll post a link to a blog that we've written that addresses that subject and references a number of important people in the field talking about it. So thanks for asking that question. That's very important here, is that the machine learning only knows really, machine learning in this form, the supervised learning problem generally only knows about correlation. That's all it's trying to exploit here.
Thanks. Eric was also raising his virtual hand, so I'm going to unmute Eric. Eric, you are now unmuted, so if you want to discuss anything directly with Charles, you can go ahead.
Yeah, perfect. Just one additional note maybe to this to your answer. I just think of so I know that what I was thinking of was that you can't just use the data in the machine learning process, as you mentioned, but maybe I see in this whole tree view one thing what I think it's not matching to my causality, or it's not. I think it's not causal that use this in this tree diagram, and maybe I want to remove it. Is it possible in BigML to say, okay, I don't want to use this data, or I just have to, or I need to prepare the data before I make the diagram or run the diagram or anything else? Do you know what I mean?
Yeah. So what you want to be able to do essentially is edit the tree, right?
Yeah, it's like to change something in the tree and say, hey, okay, I definitely don't want to have, I don't know, the shoe size in my model, and I want to remove this from this tree diagram because it doesn't, make sense to include this into a result set or something like this.
Yeah, this is something that's pretty common. People ask for this a fair amount. It's not something that's possible right now on the platform. It's something that we are working on. Hopefully, this is something that's going to deploy. I'm not sure how far along it is, but sometime in the next months or so, that will start to offer this feature. But yes, in the meanwhile, you're right that the other way around it is just to prepare the data so that you don't have this feature that you don't want. But yeah, hopefully sometime in the near future we'll offer that feature.
Okay, thank you.
Mm-hmm.
And we do have another question from Manfred Munro. He's asking if this tool, if BigML, use operations like bill amount minutes used or so automatically?
Say that one more time.
Will this tool use operations like bill amount minutes used or so automatically? I think he's also raising his, yes, he's, let me unmute Manfred. You can talk now, Manfred.
Hi, thanks for giving me the opportunity to ask this. My question was whether this tool would be able to operate columns like, for example, bill amount per month divided by minutes used per month or so automatically to find those type of correlations as well.
Mm-hmm. So there's a few things to kind of unpack there. First of all, we do offer a little macro language that allows you to engineer those features yourself. So if you yourself say, hey, you know what might be useful is this divided by this, then we offer kind of an easy way with the platform to say, create a new data set that also has this feature, which is this feature divided by this feature. So you can specify manually within the platform some of those features. You don't have to do this. You don't have to do it in data preprocessing. You can actually do it in the platform. As far as like automated feature engineering, for decision tree algorithms, that doesn't really happen. For these decision trees, they're kind of optimized for speed, and so they're not considering like a whole bunch of different engineered features. Some of the other algorithms that we offer in the platform will implicitly try those sorts of features. So for example, the deep neural network models, depending on how you depending on the topology of the model that you consider, it will implicitly engineer features like this that are, simple products of features or simple differences of features. The problem with that, maybe from your perspective, is that you're not going to see that feature in the model. You don't get to see it. It's just something that the model is trying under the hood, essentially. Okay. So that is satisfying in one way because it's trying many different thousands of things, but it's unsatisfying in another way is that you don't get to see every single one. Okay. But if you have the suspicion personally that, oh, there's this feature that's probably very meaningful and you want to engineer it, you can do that in the platform.
Okay, thanks.
Okay, and so the last thing I'm going to talk about today, there are more slides here, but I can get to those slides next time. The last thing I want to talk about today is the field importance. So this is something that people find. Oh, and here's a little bit of mathematics about how that confidence calculation works if you're very curious about it. But yeah, the last thing I'll talk about is the field importance. And a lot of times people want to know when they build one of these models or any model in BigML, they want to know which of the fields that they provided, which of their data set columns are driving the prediction, right? And why might you want to know which fields are the most important? Well, first of all, you can improve your own data collection. If you find that certain types of fields are very informative for the prediction, you might want to collect more of that type of data. Similarly, if you find that some of the fields that you're collecting make no difference at all, you might not want to collect that data anymore, especially if it costs a lot of money to collect that data. You might want to reduce the number of features in your model. If you eliminate all this data that's not very important, you can have smaller data sets, and in general, smaller data sets run faster, and so you can iterate more quickly. You can retrain your model more often. And so field importance, sort of like the prediction confidence calculation, depends on two things. The first one is the number of times that the node uses, the number of nodes that use that feature for the threshold, and then how much it matters when it's used. So essentially, every time you split on a field, your subsets, your data subsets that are defined by those fields get more and more pure, right? Until you're at the bottom and you've got only pure subsets at the bottom. So you're trying to figure out how much each node contributes to that purity. How much more pure does each subset get as you work your way down the tree? And so this is the field importance calculation for trees. For other models, it's different. But in general, that's the spirit of the calculation, is that you're trying to figure out how much each feature contributes to the overall accuracy of the model. Some people get a little confused by this because it's not kind of a It's not a general measure of importance. We're not talking about, you're not measuring correlation between this feature and your objective. It's not necessarily saying that one feature is very predictive of the objective. What it's saying is that the model relies on this feature. And so that's what you're measuring here, is how important the model thinks the feature is, not how important it is generally. And so here, if I go back to my model, when I go up to model summary report, the little clipboard in the corner here, the first thing I get is this feature importance graph. And so this says, you know, sort of by these arbitrary percentages, last month's bill is fairly important here. And then the minutes used is not as important as the last month's bill in this data. And then the other two features are somewhere in the middle. So this is basically what you get with any model that we're able to calculate the feature importance for. This is what that plot looks like. All right, I see my hour and a half is up. And so I am going to stop here. So we have maybe just a few minutes for extra questions if there are things that people wanted to ask. And I will get to the rest of this stuff at the beginning of the next session. I'll start with evaluations when we resume. So are there any other questions for me?
So we don't have any questions now in the questions box, but please feel free to raise your virtual hand and I will unmute you so you can discuss anything directly with the lecturer.
And also, if you have questions that you think of later, maybe you're watching this video on your own time later on, and you think, oh, he didn't cover X, and just as a general compliment to you folks out there, all of the questions that you've asked are ones that a lot of people ask, that the professionals ask themselves when they're doing this work. So you guys all seem to be basically on the right track to understanding this stuff very, very well.
Well, Charles, looks like there are no more questions for now. Thank you all very much for joining the first personalized session for A1 Digital. And we will have the second session next week, same time, next Tuesday. Thank you very much.